Okay, in this video we're going to look at problem number 90 in the problem set, and it deals with a conical tank, vertex down, like we have in the picture here, and it is 12 feet across the top and 18 feet deep, like such. And the 12 feet across the top will tell us that the radius of that cone, the radius of the base of that cone, or the top of the cone in this case, is 6. And so we have a radius of 6 and a height of 18 for this inverted cone or upside down conical tank. Now within this cone, water is pouring in, and it is pouring in at the rate of 9 cubic feet per minute. And in this case, 9 cubic feet per minute is the rate of change of volume with respect to time. That means it's a derivative. It's the rate at which the volume is increasing over time, or the rate at which the volume of water is being added into the conical tank. So we write down dV dt, that's the rate of change of volume with respect to time, which is a derivative. And we're trying to find out what the rate of change of the height of the water in the tank is with respect to time, at the instant that the height or the depth of the water in the tank is 6 feet. So here we have the problem set up. We have made a diagram. We've written down our givens, the rates that were given and the rates that we're looking for. And we need to now find a formula that is going to relate the rates that are given and the rates that we're trying to find. And obviously that's going to be the volume of a cone, which is V equals 1/3 pi r squared h. We do have two variables here, so we're not going to be able to continue like that. We're going to need to be able to swap out one of our variables. And how do we know which one to swap out? We have to look at what we're trying to find. In this case, we're trying to find the rate of change of height with respect to time, and we're given height, so we want to swap out radius in terms of height, and then we should be able to solve this problem. Now each time you do this, it may be something different, but here we want to swap out radius in terms of height. Now to do this, we're going to set up a system of similar triangles, and we know that for the larger triangle the base is 6 and its height is 18. The radius of the the base of the smaller triangle is the radius of the water in the cone, and that radius is changing, so we're going to call that R. And the depth of the water, or the height of the water in the cone, is also changing, so we're going to call that H. And that leaves us with the proportion R is to H as 6 is to 18, or 1/3. Multiplying both sides or cross multiplying, we get 3r equals h, and r is equal to h over 3. So we're going to go back to our original equation, or formula, which is v equals 1/3 pi r squared h, and substitute h over 3 for r, and not forgetting to square the radius, or h over 3. When we simplify that out, we get v is equal to pi over 27 h cubed. At this time, we're ready to differentiate both sides implicitly with respect to time, since both volume and height are functions of time. And we end up with dV dt is equal to pi over 9 h squared. We know that dV dt is 9, and we know that h is 6 at the instant we're trying to find out the rate of change of height, and 6 squared is 36. Sorry, I missed the most important part. When we differentiate with respect to height, we need to have a dH dt, since we're differentiating with respect to time. And finally, we get 9 is 4 pi dH dt, or dH dt is 9 over 4 pi, which is answer C. Okay, and so this is how we do problem number 90. Don't forget to differentiate with respect. When we differentiate with respect to time, we have to add a dH dt onto the end of that.